Right, so having discussed strings compactified on a circle, I want to generalize that to considering the case where the space-time is a manifold, which might be Minkowski space across an n-torus. And let's suppose we're talking about the Bosonic theory, so the total dimension will be 26. And we'll have coordinates x mu on m and y alpha on Tn. And then we could take the metric to have the form a metric on M, a metric on the torus, G alpha beta, and then we can have some off-diagonal terms A. So we'll suppose that these depend only on x mu. Then we have a metric on M, and we have G alpha beta of x, which don't carry any space-time indices. So these represent scalar fields which carry these indices alpha and beta. So it's a symmetric matrix. Alpha and beta run from 1 to n. So there are n plus 1 over 2 scalars, and then there are the A mu alpha represent n vector fields. A mu is a vector index on the on the manifold M, and alpha runs from 1 to n, so there are n vector fields. And we could put this ansatz in the Einstein action and dimensionally reduce and get an action for the metric, the scalar fields, and the vector fields. And we'll do that in a moment. But one of the things we might expect is a GLNR symmetry. So if we're suppressing all dependence on the y's, then we could just as well as have this as being Rn instead of Tn, if we're just going to focus on the y-independent modes. And if we had Rn, then there'd be a symmetry under which y alpha, the transformation under which this went to some matrix L alpha beta acting on y beta, an invertible matrix or an element of SLNR. And from this, if we have, we would expect then to be a symmetry of this kind where all upper indices transformed in this way with an L, all lower indices transformed with an L inverse, so that, for example, A mu alpha went to L inverse alpha beta A mu beta. And we might expect this to be a symmetry of the dimensionally reduced theory. So so now if we have a look at what actually happens when you do the dimensional reduction, if we start off with an action for gravity in the higher dimension, it turns out that for this is actually useful to include the dilaton in the action. So we have both a dilaton, which has this characteristic term e to the minus 2 phi appearing there, and a dilaton kinetic term. So we'll see this action, this form of part of the action again and again. And we take this action, so we're integrating over the coordinates dx of m and the coordinates y of the torus, which where k here is the torus, the n-dimensional torus. So the ansatz we have for the metric is almost what we had on the last slide, but in fact it turns out to be useful to introduce an extra term involving a squared here. If we didn't, we could do the calculation without that ansatz, and then we'd find that the resulting answer would have been rather messy, and there'd be some unpleasant looking terms, which we'd, after a lot of work, we'd find could be absorbed into a redefinition, a field redefinition of the metric to absorb an A squared term. And it saves us a lot of time to putting this in the middle. And this can be thought of as arising from choosing a vielbein, so which is the sort of square root of this metric, given in terms of the vielbein for this metric and a vielbein for this metric, and a zero here and an off-diagonal term involving E. So then squaring that will give the A squared term. But as a result of a long calculation, if you substitute this ansatz into this action, one gets a very nice answer, which has a sum of these terms. So where this phi is related to the original phi by a shift by involving the determinant of this part of the metric here. So we have the Einstein term for the this metric here, as one would expect from the dimensional reduction. One has a scalar kinetic term coming from that straightforwardly. And for the vector fields, it turns out that the action one gets has this form. So here, F is the field strength for the vector field for A with an index upstairs. And this A with an index upstairs is obtained by acting on this with the inverse of this metric to raise the index, as one might expect. And it turns out that if we treat the A with an upper index as the fundamental field, so that this A here is really G lowering the index on this fundamental object, then the thing could be written nicely in terms of this F field, of this field strength F. And here we see that because the indices are contracted upper to upper, lower to upper in both cases, if we have the F's transforming with the a GLNR transformation with the matrix L, and the G transforming with the L inverse, then this term is invariant under GLNR. And similarly, this term involving G is a kinetic term for these scalar fields G. But notice that here we've got the indices upstairs, and this means that this is the inverse of the metric with the indices downstairs. And now a little bit of thought shows that then under a GLNR transformation with a constant matrix L of the kind we had on the last slide, that this will again be invariant under the GLNR transformations, again because we've got lower indices contracted with upper indices. So we have a GLNR symmetry, and if we hadn't have included the dilaton and then this shift, there would have been some extra terms in this action which would have involved the determinant of G appearing in here. So that's one of the reasons why it turns out to be simpler to do this. So now let's another page. So now let's introduce, let's suppose we now want to consider the case where we have an N torus where we have the Y alpha now identified with Y alpha plus 1. I could have put 2 pi here or 2 pi r, but it turns out to be useful to think about this to have a 1 here to simplify, to avoid some 2 pi's in some other formulae. Here, instead of having the radius appearing in the periodicity, it's now appearing in the metric here, so that this part of the metric will include the radii of each of the n circles, the diagonal. So if we have so G alpha beta would have R1 squared, R2 squared, the radii of each of the n circles appearing diagonally, and the off-diagonal terms would represent the angles between the different circles. So this periodicity could be said that really we've got y alpha is y alpha plus any identified with any set of integers n alpha. So now we could look at this, the theory in this case, this dimension reduction, and now we'd for each circle we'd have a Fourier expansion, and so we'd have the zero modes, which are independent of y, which would be of the kind we saw in the last slide, plus an infinite tower of Kaluza-Klein modes corresponding to the higher Fourier modes, and with higher and higher masses. But now we see that the GLNR symmetries, if we consider y alpha going to L alpha beta y beta, if we want to preserve the periodicity, for the periodicity to be preserved, we require that L alpha beta n beta is a set of integers, is some n primed alpha, so where these are integers. A little bit of thought shows that then the only way you can guarantee this for all possible choices of n here is that require that each component L alpha beta should be an integer. So require the L to be a matrix which has got each entry is an integer. We see that we want integer valued elements of GLNR. The set of all integer valued elements in fact form a group, a discrete group, which is called GLNZ. So we're requiring this to be a matrix of integers, which is in fact invertible, and its inverse is also a matrix of integers. And this is in fact is the symmetry of the compactified So as he's acting on the y's, the coordinates as a linear transformation, this is a coordinate transformation. So in other words, this is a diffeomorphism of Tn. And so the fact that it's a diffeomorphism means that it should be expected to be a symmetry in the theory of gravity. So that's not, from that point of view, it's not a surprise. But it is saying this, that something rather interesting. We're getting an infinite discrete symmetry group as a symmetry of this theory. And these diffeomorphisms of the N torus are in fact not ones which are continuously connected to the identity. In other words, they're not given by exponentiating an infinitesimal transformation. And so they're sometimes referred to as large diffeomorphisms. They're large diffeomorphisms of the N torus. The large meaning is just referring to the fact that they're not continuously connected to the identity. So if we now think about the so the scalars are matrices G alpha beta, So from one point of view, so if this was a constant, then this would be telling us this is the metric on the torus. So this these provide the moduli of Tn. So they tell you about the radii of the circles, the angles between them. So these are the parameters which parameterize the geometry of the torus. And the fact that they're scalar fields means that we're allowing the possibility for the shape and geometry and shape and size of the torus to vary as we vary over the manifold M. So having these as x dependent means that these give x independent moduli of Tn, sort of x dependent moduli of the N torus. These scalars in fact parameterize a coset space, which is the coset of the general linear group GLNR over ON. And we can see this by writing G alpha beta as in terms of a field bind, so we can introduce E alpha A E beta B delta AB. So we have a field bind, and these E's are in fact invertible matrices n by n, so they're elements of GLNR. So we can think of the G's as generated from the identity matrix by acting with a GLNR transformation E of this kind. However, not all E's act on this. There's a subgroup of GLNR which leaves the metric invariant. There's a subgroup which is ON, which are the GLNR transformations which leave delta AB invariant. So they're said to stabilize delta AB. So, standard group theory then tells us that that the geometry of this space could be given by the group GLNR, but taking the coset of that by ON, the stabilizer of a particular this delta AB. So we see that this is the moduli space of the N torus, and more precisely, one should really be taking the quotient of this by the action of GLNZ, the discrete subgroup, because each element of this coset, if they're related by a large diffeomorphism of this kind, it represents the same torus. But here we see we're identifying the moduli space, and we have that an action of the group GLNZ acting on the parameters of this moduli space. So let me now turn to enlarging this a little and introducing also a B field. BMN on the manifold, which will then decompose into a B field on the manifold, a further set of n vector fields, and a set of scalars, B alpha beta. So we get a half n minus 1 further scalars, B alpha beta. We have an antisymmetric tensor field B mu nu, and we have a further n vectors, vector fields B mu alpha. So if we were to consider dimensionally reducing the theory with a dilaton, a metric, and a B field, then the reduction to the gravity theory gives a theory with a metric, a B field, and a dilaton, and then we have vector fields, A mu alpha and B mu alpha. So we have n plus n of those. And then we have a further set of scalar fields, G alpha beta and B alpha beta. This is a symmetric matrix, this is an antisymmetric matrix, and if you adding these together, we get a total of n squared scalars. And as before, we would expect this to be invariant under an action of GLNR if we look at the y-independent fields. But in fact, there's a much larger symmetry. This comes as very much as a surprise, but a careful calculation shows that the on M has an ONN symmetry. So this is the group of 2n by 2n matrices which preserve an indefinite metric of signature n comma n. And under this, the A mu and the B mu alpha, of which there are 2n of these, transform as a 2n dimensional representation. And it turns out that the n squared scalars transform as parameterize a coset space, which is ON n over ON cross ON. So this ONN contains the GLNR symmetry we would expect, and this coset space contains the coset space representing the metric degrees of freedom that we talked about before. And the vector fields A coupled to the momentum modes, the Kaluza-Klein modes, and the B fields coupled to the winding modes. And so that results in the fact that the momenta P alpha and the winding modes, or W alpha, also transform as a 2n dimensional representation. So we saw before that the coordinates and hence the conjugate momentum, the y's transform naturally under GLN, and the w's the winding modes, the winding numbers will also transform under GLN. And these are 2n. We've also seen that these will necessarily be quantized. We've seen that the momentum modes will be integers. We saw that so these are each element of these will be integers in the way we've set things up, and as a result of that, so these are the momentum numbers and the winding numbers that we saw before, and then as a result of that, the symmetry of the dimensionally reduced theory, the ONN, is broken down to at most ONNZ. So the zero modes or massless modes have that theory alone has an ONN symmetry. If we include the Kaluza-Klein modes, we know that the GLN R subgroup is broken down to GLN Z. And in fact, if we include also the ONN, if we also include the winding modes, string winding modes, we see that it suggests that the ONNZ is at most broken down to ONNZ, which are integer valued matrices in ONN. In other words, elements of ONN in which every component of that matrix is an integer, and whose inverse is also an integer valued matrix. So what this is showing is it's not showing that ONNZ is a symmetry. What it's showing is that if there is a symmetry, it will be at most ONNZ, because the symmetry would have to be a symmetry of the at least of the zero mode part of the theory, the massless modes, of which the maximal symmetry is ONN, and then there would actually, if we include the momentum modes and winding modes, the most it could be is the subgroup of that with integer valued matrices. So that means that the is at most ONN Z. But what we've seen, but we know that the theory should have a GLN Z symmetry. So we expect it to have that, because this is just a part of the diffeomorphism symmetry, the set of diffeos on the large diffeomorphisms on the sphere, on the torus. We would also expect a T-duality for each of the n S1s, so n different T-dualities, one for each of the n circles, which would take the radius to 1 over the radius for each of those. And that there's also a symmetry under which B alpha beta goes to B alpha beta plus some constants, which are some constants n, where these are integer valued. And one can show that if one does this leaves the quantization of these integers, means that it leaves the path integral invariant. And so in the world, it's easy to see that this is a symmetry of the worldsheet formulation of the theory in the quantum theory, provided these are integers. And these three sets of transformations what's called the Tutuality Group, ONN Z. So what this is saying is that the theory of the string theory compactified on a circle has a symmetry group which map a set of transformations which map the theory to itself, which is given by this discrete group ONNZ. And what this transformation does, these transformations do, is they act on the moduli. In particular, they act on the radii. So they have transformations which move you around the moduli space. They will change. They could, for example, the T-dualities will change a radius to 1 over the radius. They'll act on the moduli for the B field, the B alpha beta. the moduli space is this coset space cross the total moduli space is ON n over ON cross ON times a factor of R corresponding to the dilaton phi. So here we have these which represent the metric and the B field on the torus. The moduli in this part of the space represent the metric and the B field on the torus, and this represents the dilaton. They correspond to scalar fields because these can vary over these can depend on the coordinates x of m, and so they vary over m. And as a result, we get a picture where we have the ONN acting on this moduli space. So the natural action of ONN, and hence of ONNZ on this moduli space, acting on with ONNZ will move you from one point in this moduli space to another, will move you from a small circle to a large circle, for example. And it will also act on these vectors. It will change, it will rotate the A's and the B's into each other. And this is rather interesting from the point of view of the total space, the manifold across the torus, because this is relating, these are transformations which will relate, the A's were components of the metric and the B's were components of the B field. So these transformations are doing something rather interesting. They're mixing together the metric and the B field in a rather controlled way. So that if you act with this T-duality, with such T-dualities, you can change both the geometry and it turns out even the topology of the space. And there's some very interesting examples of that. So what we're seeing is that string theory on two backgrounds which are related by a T-duality transformation, an element of ONNZ, represent the same string theory, but represented in different ways, represented in terms of strings moving on a large circle or on a small circle. And some of the transformations, the GLNZ transformations, are diffeomorphisms and just move you, and so they just would correspond to having the same string theory, but in two different sets of coordinate systems on the torus. So this gives a very nice picture of the T-duality symmetry. And to establish this in more detail, one needs to understand, as I mentioned in the last part of the talk, the T-duality through each S1. And this could be proved rigorously within perturbative string theory, and also the understanding the shift of the B field. And both of these are things which are addressed in the example sheet. So I'll stop this part of the recording here, and I'll continue in the next part in a moment.